Okay, so when we refer to the zeros of a function, the zeros of the function are the values for x when the output is 0. And remember that when we say the output is 0, that means that the y is equal to 0. So if we set the function equal to 0 and then we solve for x. So that's kind of how we're going to do it. We're going to set the function, this is actually on the next page. We're going to set the function equal to 0 and then we're going to solve. The zeros of a function also have some other names. They are also called the x-intercepts because remember that if something has a 0 for the y, if an ordered pair has a 0 for the y, then it will be crossing the x-axis. It would be on the x-axis. So the zeros are also called the x-intercepts. They are also called the solutions. And they're also called the roots of the equation, or the roots of the function. So we could use those words like this. The next part says identify the zeros of each function given the graph. That's the same thing as if I asked you identify the x-intercepts, which the x-intercepts makes a lot of sense when we're looking at a graph. Notice on these graphs, instead of labeling the vertical axis as y, they have it labeled as f of x. So just to keep in mind, as we talked about yesterday, that f of x, that function notation for output, means the same thing as if we wrote a y. So we do not need to write down the equation or figure out the equation. We're just going to identify the zeros given the graph. And remember, for the graph, the most obvious way to associate it is thinking about the x-intercepts. So we're thinking of where does the graph intersect the x-axis. So for number 1, it would be 2. Okay, right there. Or we could say 2, 0 as an ordered pair. Notice it has 0 for the y. So we can have more than one, because in this case, for example, that parabola crosses the x-axis in 2 places. So we would have -2 and 1. I would be careful about writing the -2 and 1 with a comma because it could be misinterpreted as being an ordered pair and being a point instead. So I usually just go ahead and write out the word and. So only concerned about where it's crossing the x-axis. 1, 2, 3. Again, it could be given as an ordered pair, or you might just say x equals 3. So we're identifying those x values when the y is 0. So I could say x is -4, and also x, what would the other 0 be when x is 1? Because that's where it crosses. So far we've seen ones with just 1 and ones with 2. We had 2 that had 2. We can have even more than that. As we look down at the other ones on this page, we see number 5 has 2, but number 6 has 3 zeros. It crosses the x-axis 3 times. So for number 5, -1 and +5. for number 6, what are my 3 zeros? Where are my 3 places? Bryce?
-5, 0, and +3.
Yes, -5, 0, and +3. Okay, so there's no big formula when we have a graph. We're just looking for where does it cross that x-axis. So what are the places, what are the x values when it crosses the x-axis? Now, if we don't have a graph, I mean, could we make a graph? Well, we could, but you would be working way harder than you need to. We're going to use the other part that I told you at the top, and that is that the x-intercept, the zeros, is when the output is equal to 0. So step 1, we're going to replace or substitute what we're going to replace f of x with 0. And then we're going to solve for x. So the entire f of x becomes a 0, so that we're setting the function equal to 0. And then we just need to solve to get x by itself. So in this case, nice short 2-step equation, we're going to add 8, and then divide by 4, so x is 2. So most of these are 2-step. You may have a little more trouble with something like number 10 with the fraction. So you can add 6 and then use your reciprocal where we multiply by the inverse, the 3/2, which would mean 3 times 6 divided by 2, so 18 divided by 2 is 9. You could also, if you prefer, you could just get rid of the fraction first. If the inverse, the reciprocal, is confusing to you, you could multiply all parts by 3. Then we would have 0 is equal to 2x minus 18. And then you could solve that. Add 18, divide by 2. We still come up with x is 9. And then the ones that are marked out here, toward the, well, we have some things that are marked out at the bottom. They are marked out because, one, it says do it using the graphing calculator, and we're not going to do that right now. The other is because once we get into about week 6, I think it is, about week 6, we will know how to factor. And then to solve those kind of equations, we can use factoring to solve for the zeros, the roots, the solutions. To solve, right? We're saying solve. It's also why it's called a solution. So some of you have had some past experience that you know how to do that, not necessarily graphing calculator, but you know how to do that. So we're going to go on to this page that says rate of change. And so there are some common times that we hear a rate of change, like miles per hour. Okay, so like if we're driving and we hear something like miles per hour, it's a rate. When we hear those rates, like getting paid so much money per hour, that's considered a rate of change. So the rate of change describes the change in one quantity compared to the change in the other. And typically, when we see this, when I say one and the other, the one is typically, first we're going to be thinking about the y, or the change in the dependent variable, the y, or the output, compared to the change in the x. So you might have seen this before, delta y over delta x. That triangle symbol, delta in the Greek alphabet, means change. So the change in y over the change in x. We also call this the slope of the line. Okay, so we're going to talk a lot about slope, but rate of change, the slope of the line, when we've been putting a number with our x, we knew, like when we set up word problems, we said like, oh, this one says per hour, it's going to go with the x. It's saying that many, like the pay is going to change this much for every hour. So kind of the rate of change part of it is just like thinking of slope within an application. So slope is written as a ratio, typically in a fraction form. So a ratio of the vertical change, which is what we get when we subtract the y's. And you could go first point to second point or second point to first point. And the horizontal change. If you are used to seeing that formula with the 2 first and then the 1, trust me that it is the same, because you could call either point first point or second point. It is going to be important that we are consistent. So when we have a line, this ratio should remain equal. So if it's a straight line, the slope stays the same. If it goes up 2 over 1, it should continue going up 2 over 1. If it would change, then you could not connect with one straight line. So the slope should be written as a fraction in simplest form. So in other words, in simplest form, meaning that we need to reduce the fraction if we can. We do not want mixed numbers. And the variable that we're going to use for slope is m. Okay, the variable we will use for slope is m. So when I say in simplest form, if I had something like 14 over 4, then I should reduce, make it smaller. They're both even, so I should write 7 over 2. But we do not want to say 3.5. We don't want to say 3.5. We want to keep it where we see that the y is changing 7 for every 2 that the x changes. So it's still a comparison of two things. The only time, if it is an actual whole number, we can just write a whole number, but we understand that any whole number, for instance, if it was 12 over 4 and I write 3, we understand that this is 3 to 1, even if I don't write the 1. Okay, so I could just write a 3 or whatever if it is a whole number or an integer. But we don't want decimals. And as we're graphing, that will be a little more obvious, so that we do not want decimals. There are 4 basic types of slope. 4 basic types. Well, each one of these we're going to draw a little. This is first just going to be our little coordinate planes, little mini coordinate planes. Little mini coordinate planes. All right. We have positive slope. So this is an example that's positive slope. But this is also an example of positive slope. So with this. All of those are examples of positive slope. Notice you can have positive slope and the entire line be down in the negative numbers. What makes it positive is that from left to right, the line is going up. So if you look at it the way we read in English, if it is higher on the right than it is on the left, the slope is positive. We are going to look very much more specifically about what kind of, specifically what is the slope, but just at a glance, I know it's positive. And so then opposite of that, of course, if it's negative slope, it's going down from left to right. It could be going down more steeply, going down faster and be a steeper line, but it's decreasing. As x is getting larger, the y is getting smaller. And both positive and negative, we'll be able to get specific numbers for those. And then our other two situations is that we can have 0 as our slope, or just write the number 0, okay? And that would be if we have a horizontal line. Perfectly flat, horizontal line, the slope is 0. And then there's no other number for that, it's just 0. And then if I have a vertical line, straight up and down, then we call that slope, we say that it is undefined. I think of that as being like it is so steep, I cannot even describe how steep it is. Like just trying to climb up the sheer face of a cliff. For those last two, there's no number. If you see that it's a horizontal line, there's no math that you have to do. You can just say 0. If you see that it's a vertical line, we can simply say undefined. We don't need to count the rise or count the run. So when we look at slope on a graph, if we have the graph, instead of using a formula, I would encourage you to just count the boxes. So when we look visually, the slope is the rise over the run. The rise, that would be how much the y is changing. The run is how much the x is changing. So from this dot, they have a dot here, they have another dot here. Between those two, from left to right, it's going up. 1, 2, 3, 4, 5, 6, 7. That's my rise. And it's going over. That's my run. 1, 2, 3, 4. Can 7 over 4 reduce? No. It can't reduce. So that's my answer. That is my slope. If I see that left to right, my line is going down, like in number 2, immediately, personally, I go ahead and write down a negative because I know it's going down. And if I go from left to right, here's a dot, here's the other dot they gave me. There could be other dots I could use, but I'll go ahead and use the ones they gave me for now. It's going down 1, 2, 3. So down 3 and over 1, 2, 3, 4, 5, 6, 7, 8, 9. Does that reduce? Yes. What could I change it to? Or what could we divide by? We can divide by 3. And remember, when we're reducing, we're dividing the top and bottom by the same number, because effectively what we're doing, 3 over 3 is a 1. It's just another way to write 1. So that's why it's still equivalent. So I end up with negative 1/3. By the way, that negative sign you might see with the 1 out to the side. It's also the same as if I put it with the 3, but I usually keep it with the top unless I absolutely have to do something different. Now, if you see that it reduces, like this reduced, I should be able to start with my first dot, go down 1 and over 3, and it be another perfect point, perfect corner. So if I went down 1 and over 1, 2, 3, that would get me here. Aha, okay, that's right at the corner. Down 1 over 3, also at the corner. Down 1 over 3. So if you are trying to find the slope and there are not dots on the paper, then you are wanting to count between two perfect corners. Okay, we can't try to use like some point in between that, like, I don't know exactly what that point would be. I can't use this point because it's not on a perfect corner. I don't know exactly what it is. And if you are choosing, if it was this graph and I were choosing, I would want to choose, personally, I would choose 2 points that are close together. Because if I choose them and they are close together, then I don't have to reduce. It still works if I choose all the way out here and all the way over here, but then I had to reduce. So if I choose ones that are closer together, I won't have to worry about reducing if I choose the closest. So when we get something like number 3 and number 4, regardless of the intention of whoever designed this paper, because it was not me, regardless of Gina Wilson's intent, I would not encourage you to count how many places. If you see that it is a horizontal line, then just go ahead and write 0. And you might say, okay, what if I did? Well, how much does it go up? It goes up 0 and over 4. But 0 over 4 is 0. And we should always simplify that. Don't leave me hanging with 0 over 4. That would just be 0. And when we see number 4, as soon as I see, oh, this one is a vertical, then I know this is undefined for my slope. If I do look at my points, I see that it went up 5, but it went over 0. If you tried on your calculator 5 divided by 0, it would tell you that there is an error. Okay, we cannot divide things into 0 parts. So, undefined. But you could just simply tell me undefined to start with if you see that it is straight up vertical. Right, so what about number 5? What is our slope for number 5? Someone help me. So here are my 2 dots that they gave me. So rise over run. 5 over 3. And at a glance, I can tell that it is positive, so 5 over 3, we don't need a negative sign. And number 6. So here are my 2 dots. So my rise, from left to right, it's going down 3 and over 1. So I could say negative 3 over 1. Or I could simply say negative 3. So if it is a whole number, you can give a whole number as an answer. And if you want to kind of check, like, okay, I'm pretty sure it's negative 3. If I go down 3 and over 1 again, it should be another perfect corner. In this case, it's pretty obvious. Sometimes there are some that can get like 7/5 or something, and it's like, I think this is it. So for number 7, as soon as we look at it, we can see that it's positive slope. And between the 2 dots, or if I use this point, because it's also a perfect corner, if I use my original 2 dots, up 4/2. So since 4 divides by 2, I don't need to reduce and say 2/1 first. I can just simply say 2. Or if I use that point on the y-axis, then it is just up 2/1. How about number 8? -1. Yeah, it's just, I could use both of these and reduce, or I could just see, look, it's just every point, perfect corner. So it's just going down 1 over 1, down 1 over 1, repeatedly over and over and over and over. So for number 9, -3/4. For number 10, -5. So you should start to notice when you get those whole numbers, things are steep, like -5. Look how steep that line is getting. Sometimes people get that mixed up between 1/5. But 1/5 or -1/5 would be a much gentler grade. 11, undefined. Easy ones when we get that, undefined. Except that initially, sometimes it can be hard to, oh, where's the line? Oh, I see those giant arrows. For number 12, 2/3, yes, up 2 and over 3, good. And 13, up 1, over 4, 1, here. So when you're counting, don't count where you start, you're counting like how many jumps you have to make. So like up 1, over 4 boxes. And then 14, if we use the 2 points they gave us, we have -2/4, and then yes, that would reduce to -1/2. And 15, 1/3. So if we used our original 2 dots, we would have 2/6, and Amber's right, it reduces to 1/3. And then 16, 0. Nice horizontal line is 0. So if we do not have a graph, instead we have 2 points, then we must find the slope. And we're going to do that by subtracting our y's on the top and our x's on the bottom. And the 1 and the 2 is just, usually they're more subscript than that looks. It's just first point, second point. It's not that they're squared. So slope is equal to, and then this is where you might see this written differently. It is non-negotiable that the y's are on top and the x's are on the bottom. And then whichever point you take first on the top, his partner must go on the bottom. So this also works. Same thing. In fact, it's probably more typically written the way it is on the right, but because in English we read left to right, people prefer, my students seem to prefer going from left to right, but you cannot do a mix and match within the same problem. So on number 1, I could do 1 take away 3, and then on the bottom, 1 take away 4. If there are 2 negatives in the fraction, it is positive. So if I had gone the other direction, I could have done 3 take away 1. But if I did 3 first, I would do 4 first. 4 take away 1. And then I would just be at 2/3. So in this case, that would have been a little more efficient because I wouldn't have had the simplify step. What you cannot do is say, hey, I want to take this one first because it's bigger, but then I want to take the other one first because it's bigger. You have to go in the same order. So if I choose to use 4 first on the top, and remember it has to be a y and a y. So 4 subtract -2. There is a subtraction in the formula. It does not like replace the negative on the 2 or get replaced by that negative. Since I took 4 first, his partner needs to go first on the bottom. And then be sure to carefully use your sign number rules. 4 subtract -2, 6, -2 subtract 10, -12, and then always simplify or reduce. You can put the negative with the 2, with the 1 out to the side, but if it is negative, there should only be one negative sign. So, giving me this, or that, or kind of out to the side, those are all the same. But don't get negative crazy and start putting it everywhere. And if someone had set that problem up the opposite way, they would have had -6 over +12. It's still -1/2. But we have to be careful with our sign numbers. We must remember that there is a negative within the formula. And again, the other thing is, has to be the y's that get subtracted on top because it's rise over run. My high school math teacher actually wrote rise over run, and he spelled rise with a Y. And some people started laughing. You don't know how to spell. And he was like, I'm trying to make a point to remind you. So he would write, not that, he would write rise like that over run to help us remember that the Y's belong on top. And hopefully by this point, I think we're all pretty confident knowing that our Y's are the second ones in the ordered pairs. So 5 subtract -5, -4 subtract -8. So 10, because anytime there's 2 negatives, we know it's going to go plus plus. And -4 and +8, this would be 4. And now 4 doesn't go into 10, but we know 2 goes into both of them, so 5 over 2. If you set it up the other way, you would have had -5 over -2, and you would need to simplify and get rid of. So if you see 2 negatives in your fraction, you could just erase the negative signs or rewrite it as a positive. Let's see, let's take a look at 5 and 6. They are kind of special. 9 minus 9, 5 minus 3. 9 minus 9 is 0. 0 on the top is always 0. 0 divided by anything, 0. Please do not stop and leave me to wonder if you know that or not. So don't leave it 0 over 2, just 0 for your final answer. So if you see it's going to be 0, if it's 0 on the top, you would not even need to actually do the subtraction for the bottom because we know the whole thing is 0. In contrast, 8 minus 5, negative 7, subtract negative 7, 3 is now on the top, 0 is on the bottom, and I know that that is undefined. So when I see that my x's are the same, my slope is going to be undefined because the bottom of the fraction would be 0. When I see that my y's are the same, my slope is equal to 0. And if you did make a graph, you would see that number 5 makes a horizontal line and number 6 makes a vertical line. Okay, before we look at a couple examples about going backwards, please go ahead and turn to what's numbered as page 27. It's numbered that way because if we put the packets together. On page 27, and there is some slope homework there. So since we subtract the y's on top, I did 6 subtract y. If you like to go in the other order, it still works. So 6 subtract y, and then in the bottom, I would subtract my x's. Negative 5, subtract 5. I know the answer is supposed to be equal to negative 4 over 5 because that's what they gave me over here. When you see that negative 4 over 5, make a choice. Do you want the negative to be with your 4 or with your 5? It will work out either way, but please do not use the negative sign with both numbers. And then I treat it, well, first thing I did, I don't distribute with the negative 5, negative 5. I mean, you can, but that's just like way too much. Just go ahead and do negative 5 minus 5. Simplify that to get negative 10. Then I used my algebraic proportions. Crisscross. So I had 30 subtract negative 5. And then negative 4 times negative 10 is 40. Now we've got a nice two-step equation. Subtract 30. Divide by negative 5. And the missing y is negative 2. So the y's on the top, negative 2, subtract 6. I'm plugging everything into slope formula. The x is on the bottom, negative 3, subtract x. It's going to be equal to, now if it's a whole number, then do 2 over 1. So simplify what you can, like negative 2 minus 6, make that negative 8. And you may be able to combine some of these steps. So now if I cross multiply, I have negative 8 is equal to negative 6 minus x, minus 2x, sorry, minus 2x. Because I have to distribute the 2 to both of those, even though I started to not to. Add 6 to both sides. So negative 2 is negative 2x. Divide by negative 2. And x is 1. Now if you really wanted to check yourself, then go back and put 1. If I go back and put a 1 in here, then I would have -8 over -4. And if I divide that, hooray, I do get 2. Notice I don't see the 2 initially. It's what it reduces to. So you have 3 problems at the bottom of page 27 where you are looking for the missing part. So you're going to set up the same way as we have been setting up. Subtract the y's on top, subtract the x's on bottom, equal to, well, we already know the m. So we're still plugging everything into that slope formula, but then we're using algebraic proportion, cross multiplying to solve.